Hi again, everybody. Chris Tisdale here. Thank you for joining me. Do any of you recognize this card? Okay. If you live in Sydney or some other parts of New South Wales, you might use this card quite regularly. It's called an Opal card. And I was riding our light rail tram a few days ago, and I was getting into the logo. And the logo on this Opal card tells a pretty interesting story from a geometric perspective. As you know, I've been getting into geometry the last few years. So I thought I would do a video about that and some of the amazing stuff that the Opal card logo has. And it's not just Opal cards, it's all sorts of companies and businesses use really interesting geometry in their logos. So let me share my screen with you and I can show you what's going on. So this is the Opal card logo. And essentially it's a circle with some curves inside of it, but there's a lot more to it than that. So when I was taking my ride on the light rail, I was studying this quite intensely. I must have looked a bit strange to all the other passengers. And one of the really interesting things in my opinion is the connection between these kind of crescent-shaped moon areas and a triangle that I'll show you in a minute. So let me first of all introduce some notation. So let's mark these points here, A, B, C, and D. Now, it turns out that A, B, C, D is a square that's inscribed in the circle. Okay, and you can construct that if you want to. You draw the circle first, and then you would, construct the square. And I've done some videos about that in my, like recently. All right, so if I draw this diagonal, and then I form a triangle. So basically, this triangle is taking up half the square. Okay, I've got a right-angled triangle. And here's what I'm going to claim now. This orangey red crescent moon, okay, called a lune, has the same area as this right-angled triangle. Now, that is a problem that is thousands of years old. It's not new, but it's really interesting because, or historically, it was one of the first connections that geometers made between curved shapes and straights, shapes with straight sides, so rectilinear figures. Okay, that was a big breakthrough, and like I said, it's not new, but it's really interesting. So today I thought I'd show you that connection. Okay, so let me introduce a bit more notation. Let's let the center of the circle be, say, O. And I'll just put another sort of arbitrary point on this arc, say E. Okay, so the main approach here is to let, say, the area of the triangle have area A1, the area of this sector have area A2, and the area of the lune have area A3. So A1 is area of our triangle. A2 is the area of our sector. And A3 is the area of our lune. Okay. All right. So how do we do it? Well, you might have noticed that this shape DAECD is actually a quarter of a disc. Okay. So if we can work out the radius, then we can actually find the area of this quarter disc. So why don't we let, say, the radius here be R. Okay. And so then the question is, well, that's the radius of the original circle. What about the radius of the biggest quarter circle? Well, if that's R and this is a right-angled triangle, then I can work out that this length is going to be √2 times R, and this length is also going to be √2 times R. That's just Pythagoras' theorem, right? So actually the radius is going to be, of this bigger circle, is going to be √2R. Okay. So if A1 is the area of the triangle, A2 is the area of this sector. So A1 plus A2 gives us the area of this whole quarter circle. That's just quarter times pi times this. Okay, and if we simplify that, then we'll get pi r squared on 2. Okay, so now what? Well, let's look at this semicircle or half disc. Okay, so this is a semicircle with radius r, and its area A2 plus A3. All right, so what's that going to be? It's going to be a half times pi r squared. Now, if you look closely, this and this are exactly the same. Okay, so what does that tell us? Well, this area and this area are the same, and they overlap along this sector. So, you know, essentially we want to show that this triangle's area is equal to this lune's area, right? And this is actually what's happening here. You've got the area of the triangle plus the area of the sector equals that. The area of the sector plus the area of the lune equals that. So these things are equal. So what does that tell you? It means that the area of the triangle must equal the area of the lune. Okay. So essentially what we're doing is comparing the area of a quarter of a circle with the area of a different semicircle. Okay. Now, I was fascinated on this tram ride. I probably looked really weird, but I didn't care. And I thought when I got home, I'd share it because it's interesting, because it's a logo that a lot of Sydney-siders see every day. There's a lot of geometry, a lot of interesting geometry in here. And, you know, it's not just this logo. There are lots of other companies and brands that use geometry in their logo. So what do you think? You know, have you seen these kinds of connections before? And, you know, what other logos have you seen where geometry is a very strong influence? All right, folks, good to see you again. If you have any questions, please just use the comments, and yeah, I'll be in touch soon. Bye.